Fisher projections, and we're going to jump right back in. I think we finished this one. And then after this, we're going to start another topic. I just want to finish this example. I think we did this one and we said it was R. All right. So let's do the next two stereo centers. And then I want to ask a question based on this example. And I'm going to let you do the other one. This one over here, you'll do on your own. All right. So let's do the next stereo center, which is right here. And what's the rule again for Fisher projections when we're doing the configuration? Anybody?
So if it's on the wedge, then it's the opposite, and if it's on a vertical, it's the same.
Yes. So it's horizontal. It's the opposite configuration. If it's vertical, it's the same. That's right. That's the same. It's the same configuration. So let's do this one right here. What group is going to be one on that?
We're looking at the one on the left.
Yes, the one right here that I just highlighted.
Wouldn't it be the OH?
Yes, that's one. And then for two, it's either going to be this one or this carbon. Are you following? Now, how do we determine that?
What was the question, Dr. Russell?
We're looking for the second priority group. It's going to be one of the two blue circle carbons.
Wouldn't you look at which carbon is attached to? I mean, what's attached to the each carbon?
Yes, because they're both the same, right? So we got to go to the next atom. I
think it would be the top one.
Yeah, in this case, you have a carbon that's bonded to oxygen. In this case, you have a carbon that's bonded to hydrogen, right? So it's going to be the top. So that top carbon is going to be 2.
I can't see the writing.
Right, and then by default, what is 3?
The other carbon.
Yes. So this down here is going to be 3. So if we count it to 3, oh gosh, why is my daughter calling me? She knows I'm in class. If we count it to 3, is that clockwise or counterclockwise?
Counterclockwise?
Yeah. So it will be, it's S, but because this H is horizontal, we have to call it R. I need to grab this call. Give me 1 second. I apologize for that. No stereo center, which is the one on the bottom. So let's do this one. All right. So we know the top one is R. We did that on Monday. Second one is R. What's the bottom one? Anybody got a wild guess? No? Right, so we know the OH is going to be 1. Between these two carbons right here, what do you think is going to be 2?
Wouldn't it be the top one?
And then by default, the bottom one is 3. And H is horizontal. So whatever we see, when we prioritize, whatever we see, it'll be reversed because H is horizontal. So it's 1, 2. That looks like it is 1, 2. Sorry about that. That's all. That looks clockwise, doesn't it? If you count from 1 to 2 to 3, isn't that clockwise?
Yes.
Right. So that would be R, but because it's H is horizontal, we're going to call it S. All right. Are we okay with that?
I have a question.
Go ahead.
So the top one with the oxygen double bonded, that wouldn't be a stereo center, right?
No, it's not, because the carbon right here is sp2,
Okay.
right? And
Or
remember,
Cairo center. I'm not sure. I forgot the term.
say that again.
Is it Cairo center or stereo center?
They're interchangeable.
Okay.
All right. So that example was an example of determining the configuration on a Fisher projection. All right. Here's the question. I'm gonna label it. I think it's I. So what would the enantiomer of that look like?
So all the enantiomers will be like the opposite, right? Or
Yeah.
all the chiral centers will be the opposite.
Yeah, because the enantiomer is what? What's the definition?
It's the mirror image, I believe.
You believe?
I think it's the mirror image.
I'm about to go jump off the back step. Yeah, it's the mirror image. It's the mirror image. Enantiomer is a non-superimposable mirror image. What if I ask you to draw it? Could you draw it? If we drew this one like it already is? Sorry about that. So that's the image we were just working on. How would you draw the mirror image? Anybody? Oh, no, I'll speak out at once now. We don't want the microphones to get overloaded.
Would you just like flip everything, like put the OH on the O on the
Yeah.
right?
You can do that. Let's draw it this way. Because I think this is probably the easiest way to do it. What would I put here on this carbon right here? Anybody?
So on the right it would be H, and on the left it would be OH, right?
Yes. So I would write the OH facing itself, right? Remember, this is like it's looking at itself in the mirror. Am I right?
Yes.
Yeah. So this will be here. This will be here. This will be here. And then, is that right?
Yes.
Yes.
Yeah. It's looking at itself in the mirror. When you look in the mirror, don't you see your nose first before you see the back of your head? So if this was the nose, right, it will see itself. Am I right? Yes, no, maybe.
Yeah.
All right. What's the configuration of, of each stereo center in the mirror image. It should pop just like that because we already did the original.
SSR.
Yes, S R. Who was that?
India Johnson.
Okay, nice work, India.
Thank you.
Thank you for not being scared. All right, next question, and then we're on to something else. What would a diastereomer of this look like?
It'd be the opposite of the original image.
What's the let me cut it. That way I don't have to redraw it. Just copy. What's the definition of the diastereomer again? Anybody?
It contains a chiral center that's non-superimposable, but it's not a mirror image.
Okay, so it has a chiral center, but it's not a mirror image,
Yes.
right? But it's still chiral.
Yes.
Okay. So if this is my original, what would a diastereomer look like? How do I draw it? Do I change everything?
You change one piece at a time.
Change one chiral. Who was that?
Amaria.
Thank you. You change one chiral center at a time. So if I ask you to take that Fisher projection and draw a diastereomer of it, this is what you would do. You would draw the whole thing out. I'm just going to change this one right here. Following? I changed this chiral center. It doesn't matter which one you change, but the other two are the same. You see that?
Oh, okay, and then we're gonna go to the next chiral center and change
Right.
that.
Right. To draw the next diastereomer, yes. Now here's the last question on this, and then I'm gonna recap it and remind you of what problems you need to finish. Then we need to move on to another topic. How many stereo isomers are possible for this molecule? Uh-oh, that's on the line.
Would it be 8?
8. Good. Who was that?
Christina Young.
Good. Excellent. It's 2 to the 3, right? Sorry about my 3. It's the 3 chiral centers, so you're gonna have 8 possible stereoisomers. Are we okay with that?
Yes.
All right. Any questions about it? Excuse me. So what you need to finish on your own, let me go back up to here. I'm gonna highlight it. You need to finish this problem right here, the other Fisher projection, and you're gonna do the same thing. Same thing. Draw the enantiomer. I'll write it in. I need to zoom so I can write smaller, sorry. So do this one on your own. Draw the enantiomer and then do all configurations. All right, we good with that? And then which one did I pick? Let me move back up here. I think I already labeled it. Come on. Yeah, right here. So I have these labeled. I'm gonna put the date by it. What's the date? The 10th?
It is. It's the 10th.
2. Russell. So I want you to finish these two. And I have the note there what to do. Determine the configuration and then draw the enantiomer on the ones that are highlighted in pink. And if you go to the course notes, this document is going to be in there with all the information in it. All right, we're okay?
Didn't we complete I in class?
I thought we did too.
Let me see. Yes, we did.
We did.
Yep, you're right. I'll take that one off. Was it I or L? Hold up.
I think we did I.
We did I. Yeah.
I remember doing
Yeah,
I.
yeah. We did. Because it took us all class to do it.
Yeah.
Yeah, I'm gonna take that one off. You're right. Thank you for reminding me of that. So you'll just do J, K, and L on your own. When you turn it in, we'll know what's what. All right. We got to go on to another topic now, and I sent you a video on this, dealing with pre-existing stereo centers. So let me find that right here. Yes. All right. So let me add a page and introduce this. Let's see something right quick. All right. So let's look at so anybody who watched the video, let me put a title up here. Oh, that's bad. Let me change this paperback. Sorry. That's terrible. That's even worse. All right, so the topic is dealing with pre-existing chiral centers, right, and how they affect reactivity. All right, so I think I mentioned this when we first started talking about this, about when you do a reaction with something that's chiral, and I gave you I said that if you take two things that are achiral, you get what's called a racemic mixture. Did I say that the other day? Was that last Friday or Monday?
You said it because I remember you saying it, but I don't remember when.
Right, so you get a racemic mixture. Racemic is a term used for right 50-50. Let me not just say R in this. So you get half of one stereoisomer, half of the other, with no bias and no neither one of the stereoisomers being favored. So if I take, like, for instance, something that's achiral, I'm going to get let me see. If I do a reaction to something like this, right? So this is not chiral. Why not? Somebody tell me.
Because the carbon is connected to other carbons.
And they're all identical. Is that right? See, this carbon and this carbon are the same. So it's symmetrical. So that's not chiral. And then this is also not chiral. So when I react those two together in that substitution reaction, I'm going to get out this. and I'll get out this.
Dr. Russell, can you explain again why they're not chiral?
That is not. It's that carbon where the hydroxyl group is achiral because it's got two substituents that are identical. There's no point of difference. If you keep going around the ring, you're not going to ever reach a point of difference for those two carbons that are highlighted. And remember, one of the criteria for chirality is that your chiral atom had to be bonded to 4 different substituents. Is that right?
Yes.
So if you do something like that, where you have 2 achiral things, and you do that reaction, you're going to get what's called a racemic mixture. You're going to get 50% of this, and then 50% of that. All right. So one way to induce chirality, because that's what we're talking about, is to do a reaction on something that already, it was 2 ways, but only one way we're going to discuss. So let me add a page because I don't want to try to squeeze this in. All right. And this is important. Remember all those molecules that we were looking at first, that paclitaxel molecule and Prozac and all this stuff. When you have to do chiral, when you have to form chiral centers, you need a way to do that without getting that equal mixture. You want it to be an unequal mixture. So the question is, how can we induce chirality? All right. We can do it 1 or 2 ways. One, we use what's called a Cairo Catalyst. Right. So this method is normally, come on, Russell. This method is normally called what we call asymmetric catalysis. Right. And so what you do when you're doing this method is you take a metal, some type of transition metal catalyst, and you stick like a chiral ligand on it. So let me give you an example. So if I made like a titanium, if I use like titanium as my metal, and I put a box ligand on it, and I'm gonna explain what this means in a minute. And you don't have to write all this down either, or you can just wait and write it down later.
Dr. Russell, do you mind scrolling up a bit? Or zooming out? Thank you.
Mm-hmm. Right, so one example of a chiral catalyst is something like this. Right, so you have a titanium metal, and then the ligand that's attached to it is called a box ligand. Bis oxazolene ligand. We just call it a box ligand. Right, so that kind of catalyst, if you were to add in, I'm gonna scroll up, but I'll scroll back down in a second. If you were to add in like some substrate that could bind to the catalyst, let me just. Right, you add in a substrate, bind it to the catalyst, and then you bring in some nucleophile. When it attacks the substrate, it's either going to attack, from the site that is least sterically hindered, right? So it's either going to come from the top face or the bottom face, but you can see over here this is on a wedge, and so that side is going to be blocked. So it'll have to come from the top face on this side. So if I bring the nucleophile in from the other side, that's going to be the preferred pathway, right? Because that path is the lowest in energy. It takes less energy for the nucleophile to attack from that side than it does from the other side because of the way that the substituents are set up on the ligand, right? You see one of them has the back face block, and then one of them has the front face block. So when you do a reaction like that, that's going to lead to an unequal mixture of stereoisomers, right? So you're not going to get a 50-50 mixture if you use a chiral catalyst, unless it's just bad. Like sometimes you can have a chiral catalyst and you can have everything, all the bells and whistles, and still get a racemic mixture because maybe the catalyst isn't bulky enough, or the way the substrate bonds, it bonds differently, and the reaction takes place in a way where the ligand doesn't affect it. So there are things that happen like that. But for the most part, you're not going to get a racemic mixture if you use a chiral catalyst. So that's one way to induce chirality, is to use a chiral catalyst, right? So when I say, again, let me make sure I put this here. When I say the preferred pathway, that's the lowest energy pathway, right? Right. So that's one way. The other way is to use a pre-existing chiral center. Make sure. So the second way to induce chirality is to use a chiral substrate. Or something that has a pre-existing stereo center. Right? So if I took something like let's see, I put a tert-butyl group here, right? So that's a chiral center that's present. And then if I did some reaction on here, like let's say add HCl to it, right? First of all, what am I going to get from that reaction? That's without knowing anything about anything. You remember this reaction from organic 1, yes? Where you add HCl to a double bond? Anybody remember
Alkyl
that?
halide?
Huh? Say that again.
I don't think I said it right.
What'd you say?
The alkyl halide.
Mm-hmm. It's a way to make alpha halides, you're right. But what's the outcome? Well, I get this, and I'm also going to get another isomer. All right. Anybody disagree with that? Or you just like, yeah, whatever, I don't remember it. All right, if I add HCl to an alkene, don't I get like addition of H to one carbon and Cl to the other carbon? And it's done in what's the regiochemistry? Anybody remember what that term is for where the Cl adds and where the H adds? I got lunch on that one for real. Anybody?
Is it the H adds to the least substituted and the
Mhm.
CO adds to the
Who is that?
most? Amaria.
Okay, you're right. What's the term for it? You just got lunch today. What's the term for it?
Makarvnikov.
Mm-hmm. Mm-hmm. Mm-hmm.
Woo-hoo. Yay, thank you.
Yeah, yeah. So yeah, it's Markovnikov addition, right? That's all from part one. That's not part two. One of the things that's going to trip you up is if you don't have remember in the syllabus, a working knowledge of part one. You got to have that. You got to remember something from part one. All right. So here's the thing is when I use a pre-existing stereo center, right? It's going to dictate the outcome of the reaction. Which one of those two do you think is going to be favored? All right, think about it in terms of sterics now. You think chlorine, a big fat chlorine atom, wants to be on the same side as a big fat tert butyl group? Or would they prefer to be opposite to one another?
Opposite?
They want to be opposite, right? That's energetically, the chlorine is more, the molecule is more stable when chlorine is on the opposite side of that tert butyl group, right? So this is going to be your major product. Right, that's going to be major. And then the other one is going to be what we call minor, right? Major and minor, the term we use to describe that. I don't know why there's a lag here. I apologize for that. It's called a product distribution. Let me write that down for you. Come on, you. All right, it's called product distribution. That's the ratio of products in a competitive reaction. If I can't write a U that doesn't look like an O, I'm gonna retire. Right, so in a competitive reaction, when you have two or more products, then the ratio of those products, you call it the product distribution. So it's the ratio of products in a competitive reaction. So this reaction would be considered competitive, right? Let me show you why, and then we're gonna move on to the examples. And let me just cut this instead of having to redraw it or copy it. So if I took this, come on, and I added HCl to it, how does that happen? Like, what's the mechanism? Anybody remember? You can hear a rat pee on cotton. It's so quiet up in here. Nobody remembers what happened. Okay. So you don't remember that the double bond is going to attack H and break the Cl bond. Yeah. And then make
Okay.
a, oh yeah, it's coming back now.
Just a little bit.
Okay.
That's good.
Come on now. All these A and B students up in here. Y'all should be knocking me over to give me the answer. And then what do you get as a result of that? Anybody remember when that double bond breaks?
Don't you get a lone pair?
No, you took electrons from it. So you get a carbocation.
Oh,
But God dang it. Sorry. I almost cursed. Don't tell you folks. All right, so here you get a carbocation, which really ends up being an empty p orbital on carbon. All right, so when that happens, when chlorine comes into attack, it's got basically two ways it can come, right? It can come from here. Too many electrons, hold up. I'm gonna get my life right today. It can come from here. From the same face where the tert butyl group is. Or what do you think? What's the other way it can come in? It can come from the same side as the tert butyl group, or what? It can come in from the opposite side. Right? Which one do you think costs the least amount of energy? All this was in that video, by the way.
I was gonna say that.
You should have said it.
I know, but I just didn't want to be wrong.
It's okay to be wrong now. It's better to be wrong now and get corrected than be wrong on the test. Don't you think so?
Yeah, that's true.
It's okay to be wrong because that gives me a chance to explain stuff.
Why would it be the lowest energy?
Okay, good question. So right here, see this big tert butyl group? The thing is, let me see if I can draw it a little cleaner so you can see what's actually going on. That's a huge substituent. So first of all, it's on the wedge, right? So it's facing out at you. And then those three groups are three methyl groups. Right, so it's huge. So if something is trying to come from that side, that's bad, right? It's going to cost a lot of energy because you're going to get a big steric interaction. And it's going to, and anytime you have a steric interaction present, it's going to increase the energy. So you're going to get a steric interaction here. And that is going to increase the energy. So if it comes from the opposite side where that interaction is not present, then the energy is going to be much lower. Does that make sense? I'm going to use my example that I always use. So let's say you coming to visit me. This is you, whoever you might be. And this is my dog. He's vicious. A lot of teeth. Right? So let me ask you this: if there was another way to go, would you go the other way and not have to deal with the dog? Would you go a different direction?
Yes.
Yes, because you don't want to get bit, right? And so that's what this is like. With the tert-butyl group coming out of the page, the best pathway to attack that carbocation is going to be from the opposite side of it, right? So if there's a lower energy pathway, that's what's going to happen. That's why this is the major product. Let me go back up to the top, right here, where the chlorine comes from the opposite side. You see that? That's why we call that major, because that's the lower energy pathway. So you're going to get more of that than you get of the other one. Yes or no? All right. Let's look at an example. Let's see if we can make it make sense. All right. So this is an example of using a pre-existing stereocenter to alter the product distribution of stereoisomers, right? So you got a hydroboration oxidation reaction, and it says you got two products, and the ratio is 80 to 20. All right. Can you see that? Can everybody see that?
Yes.
The ratio is
Yeah.
80 to 20. So which one is major in this case?
A.
A. Exactly. This is major, right? Because there's more of it. You get more of A than you get of B. All right. And then it says, what's the relationship between the two products? If you look at those two products, what is the relationship between them? Are they well, I should have said stereochemical relationship. Are they enantiomers or are they diastereomers?
Enantiomers.
Mm-hmm.
Diastereomers.
They're diastereomers. Can you see right here? That's the same in both of them, but the OH is different. You see that?
Yeah. Mhm.
So they're diastereomers. Right? I don't know why there's a lag in my Wi-Fi and the writing on the screen, but I apologize for that. All right. So why is the major? Why do you think? That would be question A. It says which product would you expect to be formed in the highest amount? All right, we see the percentages, but now I want to ask a question: why? Why do you think A is major? Based on what we've been talking about. Anybody? What is it about the starting material that's going to make the product distribution unequal to begin with?
One is achiral.
And then the other one is what? Which one is achiral?
The BH3.
Yes. So the alkene is chiral, isn't it? You got a chiral center next to your reactive site. Right here. Is that right? So that's where your bias is going to come from. But why do you think that the major is major? Why do you think that? What is it about the chiral center? Look at the major product and look where how the OH is oriented.
It's
Right.
easier for it to go right there
Yeah. Why? But why though? You're right, but why?
because of the double bond, and then at the end there's a steric interference because it's so big.
Let's look at it. You're right. You're in the ballpark, right?
Mhm.
Yep. So this is the intermediate. Let me just draw. I'm only going to draw a part of it because we're running out of time. I'm just going to put OR here. The intermediate is going to look something like this. Right, where the boron adds to one side and the H adds to the other side. But when the boron is going to be swapped out with oxygen, that's what the hydrogen peroxide is for. If you remember this reaction from part 1, right? You do the hydroboration and then that's followed up by oxidation. So when the oxidizing agent comes in, it's not coming in from the same side as this. Right, the oxygen is going to have to come in from the opposite side. So if this is blocking the back face, right, so your oxygen is going to come from, I'm just going to put oxygen in brackets because it's not a simple oxygenation, but it's going to come from the front face. I'm just going to put it comes in opposite. Right, that's why you see the A as the major product, because the oxygen prefers to come in opposite to where the substituent, the chiral center is right here. Right, that's going to dictate everything. That's going to dictate how oxygen comes in and which product is formed in the highest amount. If the oxygen is coming in opposite, what does that mean for the energy? Is it higher or lower?
Higher.
If it's coming opposite of,
Oh, I'm sorry, lower.
it should be lower, right? That's your lower energy pathway. All right, we're going to stop here. Say again. It should be lower, right? Yes. Yeah, so when oxygen comes in opposite, that should be your lower energy pathway, right? That should give you your major product. All right, we're gonna stop here. If you haven't watched this video already, you need to watch it. On Friday, we're gonna finish this, and then I have another worksheet that we're gonna work on. So you need to, if you haven't watched this already, you need to watch it. I sent it out Monday, I think. All right, and then we'll pick back up on Friday.
Dr. Russell,
Yes.
is this worksheet right here, is this on Blackboard already?
Yes, it's in the assignments folder. Under it's in the assignments, and then in class handout submission, and there's stereochemistry assignment 2, I think.
Okay, and we have to turn this in?
You will, yes.
Okay.
All right. Any other questions? All right. I'm gonna stop the meeting and I'll post the notes and I'll post the recording, and I'll see y'all on Friday.
Thank you.
All right. Have a good day.